A very warm good evening to all of you. Welcome to the 156th session of Centaur's webinar series for teachers. I hope all of you are keeping safe and staying healthy. The topic for today's webinar is teaching math using visualization, and the facilitator for this session is Miss Rajeshwari Subramanian. A very warm welcome to you, ma'am. A brief about our facilitator today. She's a passionate math teacher with 21 years of experience. She had been the head of math department in premier institutions and in various boards. Currently, she's working as a vice principal in Shraddha Children's Academy, Chennai. She believes in lifelong learning, acknowledged the teaching community for implementing innovative teaching methods in mathematics. A very warm welcome to you, ma'am. Before I hand over the session to you, to ma'am, I would like to inform all the teachers that they will receive participation certificates for the session. So please do fill out the feedback form that will be shared with you towards the end of the session. Ma'am, over to you.
Thank you, Harsha. I thank Center for this opportunity. Good evening, my dear friends, teachers, and my students. I'm very grateful and appreciative of each and every one of you who's here for joining me at this time of the day after the entire day's work. It shows your dedication and interest towards the subject. In today's session, teachers, I would like to share with you some of the learnings and learning experiences which I have gathered through the years. Of course, none of this are my own inventions, I would say. It's all that I have learned through my experience and from my gurus. Without wasting your time in this evening, let me start with today's session. Today, we're going to see on how we can make math learning better through visualization. I'll spell out some few concepts or terms which are related to mathematics. I would like all of you to reflect on what comes first to your mind when I say these words. Don't think too much, just go with the first thought. As a first thought, just reflect on what comes to your mind as and when I say these words or the concepts or terms. Are we ready to go? Shall I have some thumbs up in the chat box? Waiting for some thumbs up in the chat box. Shall I go ahead? Okay. Yes. So the first, thank you, Mangalama. So the first we go with multiplication table of 2. Division. What comes to your mind first? Prime numbers. Just think it and reflect on. You don't have to give me the responses. Just think it. Prime numbers. Just think on it. HCF and LCM. Matrix transformation. Integration. Okay. So something must have come to your mind when I told these concepts or terms related to mathematics. When I told about the mathematical multiplication table of 2, generally what comes to our mind is a table, something which looks like this. Or is that you visualized something which always comes in a pair? Are we visualizing a table which is written with numbers? Or are we visualizing something which appears in a pair? When I'm saying division, is that the division symbol which comes to your mind? Or is there something like a procedure of division which comes to your mind? Now, division is one particular concept where many of you will see the children go wrong with it. Even at the age of 16, as big as 16, you'll see that children make very simple errors in division. Say, for example, if I say 210 divided by 2, can you tell me what incorrect answers are given very often by children? 210 divided by 2. Can you tell me some incorrect answer which children generally give for this? Give it on the chat box. Tell me one or two incorrect answers which are given for 210. Yes, yes, teachers, you're right. 15 is the answer which children give for 210 divided by 2. Okay, why do they do this? They are saying division as a procedure. They're not thinking on two hundreds I have and I have to make it into two parts. That is not the understanding of some children. They just see that 210 divided by 2 is a procedure to be done. Similarly, when I say prime numbers, we generally concentrate on a prime number as a number which is having, itself and one is the factors. But there are so many patterns which are involved with prime numbers. These patterns later on even gives rise to very difficult concepts, very higher order concepts like fractals. LCM and HCF. When I say LCM and HCF, what comes immediately to our mind, or many of us, is that our L shaped procedure where we use some prime numbers and we give the answers. This is what comes to our mind. Or is that we are thinking of making something equal, or is that we are thinking of having equal capacities to build in a bigger capacity, or what are we thinking on when we think of LCM and HCF? When I say a matrix, what comes to the mind first? Is that a rectangular form of numbers arranged, which comes to our mind? When I say a matrix transformation, say for example, to find out a cofactor or just to do a transpose, is that we see that as a simple procedure, or are we seeing it as some of the vectors moving from their places? Is there a visual meaning which is just behind a number representation? This is what we are majorly going to think on today. Integration, a sign which looks like an F or a S, is what comes to the mind of people generally. Are we also thinking on the volume, and are we also thinking on the area part of it? Where does all this abstraction, and why do children find it very difficult to deal with math? Why do we have a math phobia term? We don't have a term called as history phobia, English phobia, because we have never heard of all these terms before. But we quite often, the word phobia is connected with math. So what is that making math very difficult? Can I have few responses on what is making math so difficult? Hello, sir. Yes. Can I have some responses on what makes math difficult for children? Formulae. Yes. Lack of basic concepts. Passed from parents. Teaching methods. Okay. Thank you. Yes. So, understanding of the basic concepts. Yes, very clear. So, many of you have given the right answer. The most thing which makes math difficult is, as you many of you are able to, yes, not able to relate to the real life. Excellent. Yes. So, we all understand what is the problem. The main abstractness of math is what is the problem. The abstractness in math starts from the number one itself. Right from the age of 3 and 2, we introduce the number 1 to the child. Or maybe before we introduce, even at home, the child learns the number 1. And how they can say the number 1 is that they've never seen a number 1 in their life before. The child of 2 or 3 years, even 2 years now, people start teaching 1, 2, 3. So the child has never seen a 1 in his life before. The child has seen amma, mommy, papa. The child has seen TV. The child has seen chair, cupboard, fan. But the child has never seen a one before. There starts our abstractness. We have, in all the classrooms of the first standards, KGs, you'll see this number chart displayed. The way number chart with 1 to 100. But are we really catering to what is mathematics? Is mathematics just about numbers, equations, formulae? or is it about understanding? Understanding mathematics, there are different ways in which we can make children understand mathematics. One such way is visualization. Today, I would like to take examples of how visualization can be used right from the smaller classes till class 12. So, I just want to give few examples which can be used ranging all the classes from the smaller classes. Now, how to do this visualization? You don't have to do something different to do visualization, because anything which is there around you has math in it. Go deep dig into anything which is around you, and what you find at last is math. So visualizing math is not very difficult, but some of the ways which can be used in visualizing math. The first one, patterns. We can see patterns in each and everything which is there around us. Fingers, our own fingers, we can use to do visualization. Using colors, grips, drawings, diagrams, manipulatives, bar diagrams, bar models, some concrete material like abacus, geoboard, graphs. We have some other materials, are not listed all of them here, but these are some of the uh, ways in which we can try and help children visualize math. Why should we do this visualization of math? Will come in a little bit later, because I expect some answers from that from you, which I'll be doing it in a little bit later. Why should we use various methods for visualizing? Is because of the perceptual variability. Each child, each person looks into a concept from a different angle. So we should try and give inputs from different angles. So let me start with an interesting story, which I always tell my children. Okay, you can think of in which class I should be saying that. There was one small child who was around 5 to 6 years old, and this child was a little bit mischievous, okay, gifted child, so gets very distracted. And the teacher told this child to find out the sum of all the numbers from 1 to 100. The child is not a very big child, okay, he's just 4 to 5 years old child, very small child. The teacher told that to find out the sum of all numbers from 1 to 100. And the teacher thought for some time the child will be quiet. But for the teacher's surprise, the child gave the answer just in seconds. What did the child do? The child did this. 1 to 100 sum is what I want to find out. The child assumed, visualized a reversed order of that, added 1 with 100, which gave 110, 99 with 2, which gave 110. So 100 times 110, and then divided the entire total by 2 to give the answer in seconds. Many of you must be knowing that who is this child. Yes, as Mangala ma'am is saying, she always does it during introduction of sequence. Yes, many of you must be knowing who's this child. Who's this? Can someone tell me if you know, if you've heard this story before? Who's this child? Someone knows? Okay. This child is none other than, yes, Vikram sir. Yes, Vikram sir. Pooja ma'am. Yes. It's none other than the great mathematician Gauss. Now, not only Gauss, Euler, Taylor, you must have heard of the Euler series, Taylor series. All this are series which had some patterns, and these mathematicians visualize these patterns right from their childhood. It's not that they started developing this theorem when they were, when they became adults. Right from their childhood, these people had a perception for patterns. Now we are giving some formulae to children and we tell them to give the answer. Are we trying to develop mathematicians and researchers in this way? Is it possible that we give a formula all the time? I'm not saying that formula, I'm not against formulae. Formulae have their own uses. Formulae has its own importance. But is it that always giving a formula going to help us? Will it help us to bring up good mathematicians? Are we going to produce researchers in this way that we only give the formula or only teach them the pattern? It's like we can give the formula, nothing wrong. Of course, every time I cannot make a child explore patterns. I need to give a formula. But at least sometimes we'll have to allow children to analyze patterns and come up with a formula. Let us allow children to imagine things. Say, for example, a simple thing, just a color paper. In this color paper, if I can just have a lot of questions using this color paper. I can just tell the child to fold it into, say, four equal parts. What are the different ways in which we can fold this into, four equal parts? What all patterns can arise when I tell the child to fold this paper into four equal parts, eight equal parts? Even now, you can think on, if I have to fold it into eight equal parts, then what different folds are possible? I just listed here two. I've just shown here two of them. But there are many other ways in which this paper can be folded, or you can think of, are there any other ways in which the paper can be folded to get eight equal parts? Or make the question complex, make it into 16 equal parts, 32 equal parts, or anything else. Give an odd number for a different way of doing it. How are you going to give the question to this child? Are these actually having any use? Is there any use of doing this paper foldings? It should always also be useful. Say, for example, let me state one use of this particular paper folding which I have stated here. Indices. The power of indices, 2 raised to 0. 2 raised to 0 is 1, or any number raised to 0 is 1. The first figure which I have stated here, the one without any folding, has no folding. No folding in the sense zero folding. So I have only one piece with me. If I fold it into, if I have one fold, if I make one fold, then I'll have two parts. So 2 power 1 is 2. One fold, two parts. Two folds, if I make two folds, 2 power 2 is 4. 3 folds, 2 raised to 3 is 8. So how many folds you have, based on that you can get the powers of indices. Yes, yes, teachers, for going along with me in the presentation and the child. Thank you for being active teachers. Yes, Niveda ma'am. So we can implement so many concepts through these patterns and allowing children to actually go with this. Now, for very smaller classes, very small classes like first standard, second standard, also we can do this. Now, this is a simple pattern: 2 stars, 3 stars, 4 stars, simple thing. But are we allowing, okay, and even something like this: 11, 22, 33, 44, 55, simple pattern. But why should we do this? Actually, you're indirectly allowing the child to learn addition and multiplication. So the first one, you see, 2 becomes 3, 3 becomes 4, 4 becomes 5. Simple addition through patterns. 11 into 2. Okay, 11 into 3. It looks like a pattern, but it actually helps us to do addition and multiplication in an interesting way. Subtraction. Subtraction is again a misunderstood concept by many people, and people make a lot of errors in subtraction. Okay, there is something called as borrowing, which is done in subtraction. Children know only about borrowing money. They've heard of borrowing money at home or somewhere else. But borrowing in subtraction, borrowing in mathematics. Yes, I'm not saying that we should not be doing the method. Of course, there are, even though we'll do visualization or whatever it is, we have to follow shorter methods. Of course, yes. But we also give a visual meaning to that so that the child doesn't make a different mistake later. Say, for example, I want to do 100 minus 12. Okay, so when I want to do 100 minus 12, it's such a difficult calculation for a small child. Okay, 100 minus 12 has to be done by making this into a 10 and then borrowing and then subtracting. Again, why am I borrowing here? Why am I borrowing in mathematics become a big problem for a child? Can we give a visual meaning to it? Can it be something like 100 dots and 12 dots, as in the first figure? Here I have 100 dots and 12 dots. Now I remove one of the dots from 100 and I remove one dot from 12. Now it becomes 99 dots and this becomes 11 dots. Now 99, sorry teachers, 99 dots I have. So you're also teaching the concept of removal from this. You're removing something. So 99 minus 11 gives me this 88. So we are not, yeah, we are teaching actually Sunita ma'am. Yes, we are teaching taking away, as Sunita ma'am is saying, as Niveda ma'am is saying. We are grouping, we are teaching grouping, we are teaching the concept of taking away instead of stating this borrowing. And I agree that every time this method cannot be done, but let's do it once or twice so that the child understands what we are doing. Similarly comes division. Say for example I have something like half divided by 1 by 4. Now half is a fraction, 1 by 4 is a fraction. The child assumes that the answer has to be a fraction. A fraction divided by a fraction has to be a fraction. So child is confused. Is the answer to be 1 by 8? Is this answer to be something else? How do I do this division? We actually teach a procedure, but still, when I change the question a little bit, 1 by 2 divided by 3, then the child gets confused. Can we give the meaning of what exactly it means? Say the first purple colored one is a 1, the next one is a half and green one is a quarter. Now I wanted to do this. I wanted to do a half divided by 1 by 4. Now I have this purple color one which is here is my half. This is the half. Okay, this is my half. And the green color one is 1 by 4 because I've divided that circle into 4 equal parts. So this is my 1 by 4. How many 1 by 4s can I place over this half? I placed two 1 by 4s to make that half. So two 1 by 4s make a half. So 1 by 4 divided by, 1 by 2 divided by 1 by 4. Okay, then it becomes 2. So can you just give a visual meaning? Okay, somebody has told that it becomes wrong when it comes to integers. We can apply a different procedure to show that. Yes. When we have 1 by 2 divided by 3, not 1 by 4, but some other 3, then we can go with a different procedure. We can have different visualization technique for different things. Now, fractions. Now, fractions are seen only as fractions. After having, in the modern age, after starting to have pizzas, many people have probably understood what is a fraction. Okay, I want a bigger fraction than my mother or a brother. So people have started understanding fractions because of pizzas, I think so. But are fractions only, this is the only way of, uh, yes, thank you, Satrina. Yeah, I'm happy that I used that. So now fractions, the first one, if you see, it's 3 by 8. Now are fractions only represented in this way? Can we have different visuals for a fraction? Now the second one, if you see, I've just put in a bar. 3 out of the 10 fractions are, 3 out of the 10 parts are shaded there. So the red color ones is 3 by 10. Now here we also bring in the concept of colors to smaller children. Say, if I make it a little more bigger, I take a 10 by 10 grid with 100 boxes in it. Okay, I put some colors here. Now, if you tell children to put in some more colors and make their own designs, children at this particular age, when they are in 5th, 4th, when they learn fractions, they are also learning about primary colors, secondary colors. So you can bring in colors. It attracts them. So you can tell children to make some patterns with some colors and say, ask them what part of this figure is What fraction is shaded with a particular color, say a green color? What is the pattern? How much is shaded with the green color? Now, this comes to fractions. Now, fractions are seen only as fractions. Can we also convert this fraction into decimal? Can we also convert this fraction into a percentage? Now, when you put in a grid which is 10 by 10 grid, that's a 100 boxes grid, automatically you bring in percentage to that. So, say for example, in this figure, I'm not counting it, I'm just saying that, say for example, some 15 of the boxes are colored in a pattern which a child did. So, 15 out of 100. 15 out of 100 can now be converted into a percentage. It is a fraction. It can be converted into decimals. So you're helping the children to link concepts. At the same time, we are also helping children in applying their own interests. So we can have an interconnection between the different concepts. Even when we are framing questions, we can give chance for the child to go wild with the imagination. Say, for example, instead of asking something like, what is the area of a rectangle which has the length as 4 and the breadth as 6, something like that. What is the area? So the child uses the formula length into breadth and gives the area. Yes, that has to be one of the questions. I'm not saying that question should never be asked. But if you give the area and tell the child to get the possible length and the breadth and represent it diagrammatically or graphically, then how many answers will the children will come up with? There will be a variety of answers that the children will come up with. They may come up with all these answers. Now, in this, if you see, the length and breadth have varied for all the figures. Yes, Shanu ma'am. Yeah, I can just see the example of a dairy milk. Yes, you're right. So your imagination right now is started flowing. You started visualizing. So we can have so many patterns. We can have so many answers which will come up from children, and this is again a pattern. There is something else which is there hidden behind the pattern. There are other concepts which automatically comes to the child's understanding. Can you just name some of the other concepts other than area which can be learned from this? Can you think of other concepts which the child will learn when we come up with this activity? Can I have some answers in the chat box? Other than area, length, and breadth, by doing this kind of a diagram, what other perimeter, multiplication, fraction? Yes, factors. Yes, factors, bar graph. Okay, fraction. Yes, there are so many other concepts. Even, let me just wait for some more actives. Place values, multiples and factors, perimeters, number line. Factors, many of you have told factors, perimeter. Okay, even they come up with the proportion. When one increases, the other one decreases. Okay, some of the concepts which I could think of is proportion, factors. Yes, even I thought of factors. Yes. Now, when we give such experience to the child, the solving of word problem will become easier for the child. When you help the child to visualize, the solving word problems will become easier, because word problems is one very big tension for children in mathematics. If we help them to do this visualization, visualizing worded problem will become very easy for them. Now, squares and cubes. When I say 2 square, 2 power 2, 3 power 2, I'm saying a 3 raised to 2. I mean, I'm saying a 3 raised to 2. Why do I call it as a square, first of all? Why should I call that as a square? What is the relation between, 3 raised to 2 and a square? Okay, say suppose I'm telling them 4 cube. 4 raised to 3 is 4 cube. Why is it a 4 cube? Why do we call it as a 4 cube? Are we just going to teach children that 3 square is 9, 4 square is 16, 5 square is 25? Are we just going to tell children this? Or are we going to tell children to memorize that? Memorize 4 cube is 64. Yes, that is also at one point required, but Why is 3 raised to 2 called as a 3 square? Why it is 9? Children have to know that if we form a square with 3 units as the side, it will have 9 boxes in it. That's why it's called as 3 square 9. Similar concepts with a cube. If I have a cube with 3 units as the side, if I make a cube, then it will have 64 boxes in it. So if we give a, 3 cube 27. So if we give such examples and help children to visualize, they will visualize a lot other things. Say for example, this pattern of 1, 4, 9, 16, 25, if you see, you can see what pattern is there in this. 1, 4, 9, 16, 25. You can see the pattern in that. You can see that 1 is added with 3 to get a 4. Now 1, 3, 5, 7, 9. These are the odd numbers, consecutive odd numbers. And 1, 4, 9, 16, 25 is square numbers. But we can see there is a relation. We can see there is a pattern in it. 1 added to 3 gives 4, 4 added to 5 gives 9, and so on. Isn't it? So we can have such patterns which will help them to invent something new. Say for example, something which is related to this itself. If you see that, say 3 square is 9. Okay, sorry. Say I have a 3 square which is 3 square is 9. Fine. So now this 3 square 9 is actually a 4 plus 5. 4, say 5 square, the next odd number. Okay. 5 square is 25, is a 12 plus 13. Just give this pattern to children, or even you think of it. Have we seen anywhere this 4, 5, and 3 together? Have we seen anywhere this 3, 4, 5? Have you ever seen them together? Have we seen this 5, 12, 13 anywhere together? Yes, teachers. Have we seen this 3, 4, and 5 together somewhere? 5, 12, and 13. Yes. Pythagorean triplet. Yes, Kaushik sir. Yes, Veena ma'am. So, we are also helping children to find patterns which can be, give them a very big concept like a Pythagoras theorem. Visualizing algebra. Yes, many of you gave me the wonderful answer of Pythagorean triplet. Now, visualize algebra. After COVID, there is a positive effect for mathematics, I would say. Mathematics has become more visual after COVID. So it has turned out to be a positive effect for math teachers, if not for others. Because there are so many manipulators online, there are so many videos online which we have not, at least I have not gone through them so much before COVID. It's only after shifting into this online classrooms, I started, studying that where are the resources for representing, an algebra concept. Because previously it was very easy with the, the models or anything else. But when we came into this COVID, we don't have any hands-on materials with us. What do I, I'm teaching online. How do I teach children with that? What am I going to do? When I started thinking on this, when we all started thinking on this, is when we found out that we have so many manipulators online. We have so many concepts explained with the help of beautiful videos online. Right from matrices, matrix transformations are beautifully shown in so many videos. Simple things like a plus b the whole cube, identities, like you can get such clear videos online, and what you have to do is that just give a courtesy, like I have given a courtesy from the site from where I have taken it. Just give a courtesy to the people who have worked on it, and fee and use all this resources available online, because it's, and even now we have almost come to a normal classroom, but still we can make use of these to give a 3D effect and make children understand this. Finger perception is something which our own Indian way of doing things, but now we feel shy to use our fingers for counting. Many of us feel shy, our children of the next generation feel shy to use their fingers and count. But finger perception, the Indian way of doing, is a very, very, very important technique. But we have stopped using it for some reason or other. One of the PhD holders, researchers in mathematics, Dr. Jo Boulder, has stated this in her research. She says that there are two spots in our brain which sees and uses the particular spot gets lightened up when we start using our fingers. It seems this is a research finding by Dr. Jo. So there are spots in our brains which get lightened up when we use our fingers to work and also just by seeing our fingers. There are many ancient methods by which we can learn trigonometric values, we can learn multiplication using our fingers. Lots and lots, your teachers, I don't have to tell you, and even the students who are present here, I don't have to tell you, lot of resources available on how we can use them. You can invent your own methods of using fingers and getting the things done. How many of you are know this Pingala? Can you tell me any responses in the chat box? Pingala, have you heard his name before? Anyone knows any contributions by Pingala? Waiting for your responses. Okay, national flag. Yeah, you're speaking about the this. Okay, one of the. Okay, yes, fine. Have you heard of Pascal? When I say Pascal, now many of you will know who is Pascal. Okay, Pascal's triangle. Yes. Okay, Pingala is one of the ancient mathematicians who gave us our Pascals. Yes, I have got so many S for Pascal, but not for our own country's Pingala, and not for that's where we have to understand that we have to advertise our findings. We have to advertise and bring to the world our findings. Our children also may come up with patterns. Our children may come up with formulae from patterns. We need to take it to the world. Some of the concepts are not reached to the world. We have to make our children, our students finding to come up to the world. Pingala is someone who has worked with Pascal's triangle. We know Pascal's triangle. Pascal's triangle has thousands, hundreds of patterns in it, hundreds of usage in it. One particular usage is to get the NCR value, the binomial coefficients, isn't it? So the binomial coefficients. Now, even for binomial coefficients, there are different ways in which you can see this particular triangle. You can use this for various classes. You can use it right from the smaller classes to the higher classes. You can start this particular Pingala triangle, or the Pascal's triangle as it is known, can be used right from the lower classes for addition till your 11th, 12th standard for the NCR value. Again, lot of 11's powers, so many things, so many patterns are available. Leave our children to explore, they'll give us 100 more patterns. Now, each and every number in this triangle is a sum of the numbers in the previous row. Many of you might be knowing this. It can also be seen as the different ways to reach a particular point. Like I want to reach this point, which I'm right now, highlighting. How many ways, how many routes are there to reach this particular point? So I want to reach this particular point. How many routes are possible? One route from here, another route from here, without crossing the others, right? So how many routes are possible? Two are possible. So if I have to reach this particular point, you can try it out. There are 10 routes possible. Like this, there are various other patterns which are possible from this. Magic squares. Magic squares are like treasures. Okay? Magic squares, say for example, can somebody tell me what is the number here? What is the magical number here? Okay, someone has asked for the slides. I'll just get in touch with. Yes, Saparna ma'am, you're the first one to click on it. It's a 34, which can be, yeah, maybe the others also, but the net permits Saparna ma'am to give the answer first. So 34 is the number here. Now, suppose I want to do a 5 by 5 magic square. What magical numbers can work? Put the question to children. If I want to do a 6 by 6 magic square, what magical numbers can work? This is the formula. Now, instead of going from n into n square plus 1 by 2, go from the magic square to the formula. Are we going from patterns to formulae, or are we going from formulae to numbers or formulae to patterns? How are we proceeding is what is the question now. Not every time possible, accepted. We have to give results, we have to complete the portion, we have to do all these things. We are expected to give 100% results, yes, but once in a while, please do it. Okay. Now, patterns which are there in puzzles and games, my favorite game, which I use for almost every workshop or webinar, is Tower of Hanoi. Okay, this is Tower of Hanoi. In Tower of Hanoi, we can increase the, it's also called as Brahma Tower, or Brahma rings or something like that, which is an Indian version. So we can have lot of patterns which takes place in it. Now, just go and see in different online resources what is Tower of Hanoi, and you get plenty of resources. Now, if the number of discs are 3, then the minimum number of moves to get this discs into another peg in the same order is 7. If I have the number of, yes, Kiranji, thank you. So n is equal to 4. That is, if I have the number of rings is 4, then to move it as it is without, there are different rules. I'm running out of time, so I want you people to explore it for yourself. Now, this 3, 7, 4, 15, are these having some patterns? We can play a game with children sometimes. I do this generally when I teach mathematical induction. When I start introducing mathematical induction in class 11, because in class 11, mathematical induction is a very abstract concept and children don't find any meaning in learning it sometimes. So I take a lot of time to, do this introduction for mathematical induction, and I always make children play this game. And further analysis, I want you people to do. Now I want some responses from your side on why should we visualize. From whatever examples, if I have given, may I have some few responses on why should we visualize? Yes, Dinesh, thank you so much. Can I have some responses in the chat box on why should we visualize? Clearing the concept helps in easy understanding, relate to real life, gain clarity. Yes, ma'am. To remove abstractness, yes, an Indian mathematician, fine. Clear and better concepts, real life understanding. Yes, strong concepts, related. Yes, thank you, teachers. Thank you so much, teachers, friends. Yes, as you all said, yes, please giving me answers, I'll see them. Abstract to concrete, interrelationship between the concepts to create interest, yes. Interrelationship between the concepts. When they see a right angle triangle in one place and see the same right angle triangle in another place. Okay, so what is the relationship? To reduce complexity, to get attention. I think you have given me almost all the answers which I have put in here. Association and enhanced memory is something which I wanted to say. I have 4 minutes to go. So when enhancing memory, when you have associations, connections between the concepts, when you connect one concept with another, when you have a visual understanding, what happens is that the synapses in your brain, the connections in the brain get more stronger. This has to be done when the child is small, like at the age of 12 and 13. This helps in better understanding, and you open lot of memory paths for them. When we see words and images, there are many visual learners in them, of course. I have 2 more minutes to go, so let me just complete whatever I planned. Even in trigonometry, in our ancient history, people saw patterns even in sun's movement. The movement of sun, it starts 0 degree east. Now, if you see many of the Indian months, okay, Indian month, it starts the first day of the Indian, sorry, the first day of the new year in in many of the Indian months. If you see different languages, different areas, it will always start when the sun is at 0 degree east. Many of them, not all of them. And sun goes to the northeast 90 degree, comes to 180 degree, comes southeast, and again sun is back to 360 degree. This is the shape of a sine curve. And this is how an Indian year goes accordingly, it seems. There are many other concepts based on the movement of sun. Sine curve is being done. Before it was called as sine curve itself, our Indian mathematicians did the sine curve. And the angles between the bow and the arrow, right from that period, they had the understanding of sine. Last but not the least, graphs are our lifeline. There are so many concepts which we can make a child understand with the help of graphs. There are many online graph making softwares available. Please go and visit them. Many of them. I've named two of them here, Desmos. But there are many other graphical designers, graphic calculators available. This particular, one of my students taught this graphs to me, I should say. We know graphs, but when I was first time teaching 11th standard mathematics, there was one child who asked me this question. I gave an answer in trigonometry or something like that. I don't remember what answer exactly. This child is asking me. It was the answer wasn't something It did not have anything related to graph. But the child asked me, "Mom, what is the graph of this?" This was the question which this child asked me. "Mom, how would the figure look like?" Actually, I didn't see any figure in that because the answer was a number or in say something like 27 pi by 3. Something was the answer. And for me, as a first timer, when I was teaching 11th standard, I was just taken back. Oh my God, does this have a graphical meaning? I started wondering where is the graphical meaning to that. Then I went home and I also took the help of the child who asked me this question. And I started thinking on, is there a graphical meaning to every answer which we get? Even the t-shirt makers have understood that there's a graphical meaning for everything. T-shirt makers have put designs on graphs, but we have to understand that and we have to implement it. There can be many concepts which can be shown with the help of graph. We just say that the differentiation of a constant is zero. Differentiation of a constant is zero. But when it comes as say, we say that differentiation of 4 is zero. But when we say 4x, the child writes that also as a zero because he sees 4 is 0. But let's make it clear that a line parallel to the x-axis is what is the graph of a constant and the slope is 0. That is why the differentiation is 0. Let's say that with the help of a figure, the child remembers it forever. Thank you, teachers. Thank you so much. Now I'm just to conclude, help children to see beyond what our eyes can see. Help children to see the inner meaning. Thank you so much. Harsha,
Uh,
can I take a few
yes, ma'am.
questions, Harsha? Yes.
Yeah. Actually, one of the teachers is telling uh, some theory can be developed by visual model. One of the teachers is
Okay.
just telling, ma'am. Yeah.
Yes, ma'am. Not only, yes, there are many other,
Yeah, all are
So it's
appreciating the
many,
session,
many
ma'am.
other theorems.
Yeah,
Thank
most of
you.
the teachers
I'm
are
seeing
appreciating
them.
the session. Yeah.
Yeah. Yeah, I'm seeing their comments. I can see some of my colleagues' comments there too. Yeah, if I have any particular questions, someone has asked for the presentation, PPT, ma'am. If there is a way to share, I'm ready to share. I don't know whether it permits. If it permits, thank you, Savitri, ma'am. Thank you so much. Yes. What software can you use for visualization? Okay. Someone has asked for software. There are many softwares which are available. The one which I have shown, the graphs one, is Desmos, which is generally used by many people. But there are many because I should not be promoting one particular brand. So you can do a research on just put in graphic calculators, you'll get in many.
Ma'am, another teacher is asking how will it help children with LD?
Yes. Thank you for asking this question. When we have learning, so now learning disability is different types. That's a separate sector, of course. In learning disability itself, what kind of a difficulty the child has, it depends on it. If the child is having dyscalculia, that is having problem with calculations, then the visual part will help. What is the particular difficulty with the child has? Okay, we generally term it as an LD, but there are different categories in that. And for some of them, definitely it will help. We can try it out with them.
Ma'am, Savitri, ma'am is asking, are you using GeoGebra?
Yes, ma'am. GeoGebra, I'm a very experimental learner. So whatever is possible, I use. Okay, whatever is known to me, of course. Whatever is, if I'm aware of something, I use. So I'm aware of GeoGebra and I've used them.
Ma'am, I think there are few more questions to come up from the teachers, I think. They are
Okay,
just
fine.
coming up with, yeah,
Okay, let them come up with the
yeah,
question.
yeah.
If I have 2 minutes time, I just missed out on a few of the
Yes,
concepts.
ma'am. Yes, ma'am. You can go
Okay,
ahead.
yeah. So yes, because I think I have some 2 minutes time. When I'm saying functions, teachers, like logarithmic function, if you say that some of the concepts are very important, which are to be stressed in the classes, say for example, log one's value, things like that. Okay, and we have to always say that a function is always a graph. A function always has a graphical representation. So if I say a log one's value, some of the very important concepts can be easily memorized and brought to the notice of the child using the graphs. So one such, because I didn't give much time to the graph part. Again, quadratic equation, we say that solution to the equation, solve the quadratic equation, solve the quadratic equation. What is solution? First of all, the child has to understand that the quadratic equation solution is the point where the graph of a quadratic means parabolic, that they have to know, and how does the curve looks like, and the point where the curve touches the x-axis, that is what is the solution. First of all, what is the solution to a quadratic equation has to be known to the child graphically. Okay, it's like if I just say that solve it, get two answers. Fine, I solved it. I got two, minus two and three as the answer, or whatever, minus three and four, something. But what does the solution actually mean? Where are we seeing this solution is very important. If the child understands that, later on it will be easy for the child to understand what is an imaginary number. Okay, where we don't have a solution, what is that called as? What if, we always used to say concepts like discriminant is zero and all those things. But if the child first of all knows that the solution, what is the solution to a quadratic equation, then all other concepts can be easily understood by the child. Now we are saying that sometimes some of the functions are not differentiable. Why not differentiable? We say that mod function is not differential, whatever. You give some examples and say that this is not differential. Why not? Give a graphical meaning. In spite of us saying many times also that this is not differentiable, the children will always have a question, or they just don't, it doesn't get registered that it's not differentiable. Why give a graphical meaning of when the function is not differentiable? So for everything, if we try to give a graphical meaning and a visual representation, then it will be very easy for us to proceed. And I just want to say last thing, math is always treated as a subject which is only for the achievers. If you are very intelligent, then only you can learn math. There's a separate, like we math teachers, okay? We math teachers are treated as somebody from the heaven and who is very, intelligent. We are just, a math teacher is a special race. A math teacher is somebody who's very great, very distant from the child. Math is some point which is very much far away from me. Only the intelligent people can do. This kind of an attitude should be first taken away. Math can be done by everybody. And we math teachers also learned it that way. None of us were born mathematicians, and we are actually math teachers, many of us, not mathematicians. So it's, how the child understands math. Every child, okay, there's nothing called as very intelligent, nothing like that. Everybody can do math. It's everybody's cup of tea. And we math teachers are one among the children, have to be understood by the children. Thank you, teachers.
Ma'am, there is a question by Mr. Dinesh Kumar. Please suggest some
Yes.
app with Playway Maths.
Okay. Dinesh sir, as in a platform, I don't think I'll be able to give one particular site. I don't know if it's correct to state one particular site as a good site, good website. Okay, it becomes like a promotion for that particular site. But there are many, sir. If you can just type out whatever concept you need. Okay, if you say, for example, you want to do some say solving a linear equation by using games. Just type this out. Just type this out in Google, you'll get hundreds of answers. You have to spend some 15 minutes time to see which is the good one. In an open platform, I don't want to name one particular site, and it will become like a promotion. But there are many.
Thank you for the reply, ma'am. There is one more query from one of the teachers. What course can I do after BCom to make my math stronger?
Um, After your BCom, okay, it depends on what is that you're wanting to be. Okay, what is your future plan? Like after learning math, what are you wanting to do? It depends upon your future plans. Okay, so after a BCom, see, even go for a BSc in mathematics. So it's not, the option is not closed, but it depends upon where are you going to use it. Are you just wanting to use it for better calculations? You can even do a Vedic math course. If you just want to improve your calculations, you can do a Vedic math course or an abacus course. What is your aim of doing after the BCom? What is the final thing you want to reach? Where do you want to reach? Based on that, is that the calculation to be improved? If you have to improve your calculation, then some course can be done. If you want to improve on the concepts, there are different courses. It depends on what is that you want to do after that.
Yes, ma'am. Thank you for that lovely
Thank you.
answer, ma'am. Uh, I think all the questions are exhausted, ma'am, right now.
Thank you so much.
Thank you, Rajeshwari, ma'am, for a very engaging and informative session for our teachers, community of teachers. I'm sure that our teachers have got a lot of takeaways from this session. Thank you so much, all the participants, for engaging with us today. To register for more such upcoming webinars, please visit my center. And yeah, thank you for joining us.